이 변화하는 기술 환경 속에서 예술가의 역할, 또 예술 지도자, 교육가 역할이 어떻게 변해야 되는지 미리 국제 창작 환경 기술 기반의 세상을 앞서서 10년, 5년 앞서서 경험해 보셨기 때문에 좀 더 귀담아 듣게 됐던 것 같습니다. 저는 너무 놀랐던 게 예술가신데 오전에 너무 재밌는 퍼포먼스를 보고 PT가 너무 논리적인 친구예요. how, 좋은 답이 되시는 것인가 생각했습니다. 지금 이 시대가 필요로 하는 문제 얘기할 때 많은 분들이 문화예술 쪽에서 예술적 감성을 가진 공학자, 테크놀로지를 잘 이해하는 예술가, 융합과 협업에 능한 소위 융합형 인재들 대부분 많이들 말씀하십니다. 그렇다면 과연 우리는 어떻게 그런 융합형 인재를 키울 수 있는지 굉장히 지금적으로 가지고 있는 궁금증입니다. 자칫 많은 분들이 우려하시 도마를 크게 잡다가 못하고 죽어만 합니다. 이런 우려도 있는데요. 그런 예술과 기술의 융합형 인재를 키우기 위해서 실제 문화예술 교육이 어떻게 이루어져야 하는지 지금 나오신 이분과 함께 그 대답을 찾아볼까 합니다. 다음 연사는 리차드 윌리엄 앨런스인데요. 앨런스는 현재 홍콩 시티대학교의 스쿨 오브 크리에이티브 미디어의 학장으로 재직하고 계시고 디스플레이나 가상현실, 증강현실, 오랫동안 시험하는 여러 가지 새로운 다양한 재미있는 예술과 기술과 그런 프로젝트를 추진하고 있는 센터 포 어플라이드 컴퓨팅 앤드 미디어의 부소장이시고 계십니다. 큰 박수로 리차드 윌리엄 학장님 무대로 모시겠습니다.
I want to thank Casey for inviting me here today. It's an honor to be here. And I'm going to speak to you about arts education. And I think the talk that I'm going to give will have nice resonance to the talk you just heard from Dr. Kim. So the School of Creative Media is celebrating its 20th anniversary. And it can be characterized as a media arts school. It was really conceived to develop a curriculum in computationally based media art, which began in 1998. At that time, traditional arts practices such as film, photography, and music production were being transformed by the digital revolution. And new areas of practice were beginning to emerge in art installation, projection mapping, sound art, software art, and so on. And the School of Creative Media really was conceived as a school to catch the wave of new media arts in Asia. Before I get into more curriculum issues, I want to say just a brief word about Jeffrey Shaw, who was the dean before me. Jeffrey is a pioneer new media artist. He was dean of the school, and he's pioneered work in the area of intangible and tangible cultural heritage in relationship to digital preservation and display. This is a work he's done on the Dunhuang Caves in China, creating a 3D, immersive, interactive environment. This is another work he did on Hakka Kung Fu, motion capturing the work of Kung Fu artists, and then finding innovative and novel ways to display this motion capture data in an installation and exhibition context. Throughout its history, the School of Creative Media, I think, has been characterized by dynamism, its capacity not only to respond to changes in the technology and creative media environment, but also to, I think, and this is key, initiate change. I think there are three main questions that have governed the development of our curriculum. The first is the kind of balance that we need to have between traditional conservatory-based education, say in film, photography, and the kind of interdisciplinary education in media practice, which allows students to develop the intermedial competence that characterizes new media art. The second is what kind of education in computation is required in order to train students to practice new media art and design, and how is that education going to be implemented? The third question, the broad question, is what is the role of science education and science in general in a technology-intensive media arts school whose curriculum are more usually governed by the blend of arts practice and liberal arts education. Obviously, the answers to these questions in our school, like any other place, develop into relationships and pragmatic constraints, institutional constraints, funding constraints, individual competence. But above all, I think they reflect a desire to develop an interdisciplinary curriculum that adjusts to and is responsive to the radically changing nature of media in the 21st century. So we have 3 undergraduate programs at the school. The first is our BSc program, which is co-taught with computer science. And this is more technical than artistic, focused on graphics, animation, and interactive game design. The second program is our BA program, which is more oriented towards making art with a digital image and sound in media such as film, photography, and new media installation. This program is really distinguished by the way it encourages experimentation and interdisciplinarity. But I'm going to focus my remarks today on a more experimental new program, which is our Bachelor of Arts and Science in New Media. And this is designed to develop a new kind of training in response to and in concert with the rapid developments in science and technology. This degree was conceived in 2012 by Dr. Hector Rodriguez, who I want to thank for collaborating with me in this talk. And he began his career as a humanities scholar and became a digital media artist. It's now run by Dr. Yulin Lam, who's a computer scientist, and computer research scientist, I should say. And she's also become a media artist. The goal of this program is to encourage students to engage creatively with new technologies and materials in a manner that's informed by science and computational thinking in order to make computer-based artworks and interactive objects. The curriculum design of the BAS is organized around 5, there may be others, but for the sake of today, I'm going to say there are 5 basic principles of the curriculum. The first is creative interdisciplinarity between art and science. The second is what we call participatory science. The third is learning by doing. Fourth is collaborative learning. And fifth is the creation of new media. So I'm going to spend the rest of the talk going through each of these and illustrating them with examples from our curriculum. So first idea, creative interdisciplinarity between art and science. The idea here is that students should not produce art vaguely inspired by science. For instance, a student might hear about the uncertainty principle of quantum mechanics and then go on to make a work about the idea of uncertainty without displaying any real understanding of the science. The BAS was designed to encourage a deeper engagement with than that, a transfer of knowledge. The aim is for students to produce works that incorporate physical materials, procedures, and concepts from non-art domains like material science or biology. Ideally, science should not only serve their artistic vision, but perhaps influence or transform that vision. This is not just a matter of learning theories. It's a matter of mastering technical skills to whatever level the student can achieve that allows any kind of theory to be realized and translated into practice. This can be less intimidating and complicated than it might appear for students who are unfamiliar with science and technology. For example, in one of her classes, Dr. Lamb teaches students the principles of magnetism and how students can use the principles of magnetism to make interesting art projects. One student used ferroliquids as a paintbrush and developed a system involving electromagnets to control the dynamic patterns of fluorofluid which drive the oil paint on the canvas. Another student hacked a magnet stirrer to control the motion of the spinning's top, which stood up from resting pose and spun continuously without falling and became an art installation. In her DIY organic solar cell workshop, students used natural dyes, such as raspberry juice, in order to make solar cells from scratch. In another course, called cymatics, Dr. Lamb teaches students the basic physics of sound, and they develop techniques to visualize sound and vibration and apply them in creative works of art. Secondly, the BAS stresses the need to make science open to public participation. As in the past, the general public lacks knowledge of contemporary science, but arguably with the development of computing, the situation has become much worse. Both the institutions where scientific work is conducted and the technologies informing science function as a black box that most people can't understand. This situation results in a deficit of democracy, where citizens are ill-informed about both the ideas and the technologies that affect every aspect of their lives. One way to tackle this condition is to develop channels of communication between science and the public, in which the artist can play a special role. Through an artistic practice informed by science, which involves learning by doing, come on to that, the layperson can make sense of science and communicate this knowledge to a wider world. This dimension of the education at School of Creative Media is exemplified in Scott Hessel's award-winning Extreme Environments project, which is about to enter its 5th iteration. This is a highly innovative arts research program in discovery-based education, where students enter a fragile, endangered environment, collect data about the environment in collaboration with scientists who are already working on site, and then they turn this data into new media artworks, game applications, interactive cinema, and photographic and video installations. The project not only provides a crucible for new kinds of environmentally influenced artwork, but new ways of presenting scientific information to the public at large. Thus far, Hessels has taken students to the Mojave Desert, to Antarctica, Vietnam caves, and to the Solomon Islands. And next year's project, he is going to take them into space. Well, not exactly. Students are going to stay on Earth to examine space. For many of the students who participate in this program, it's a life-transforming experience from which they learn about scientific inquiry and learn to make meaningful art out of that inquiry, which communicates to large numbers of people. The third principle that we try to implement in the BAS program is a constructivist conception of knowledge. That is, learning by doing, with hands-on practice. Teaching computation to students with no science background, as my colleagues here will know, is a challenge. We teach the basic concepts of media computing in a way that they can be grasped intuitively and translatable to hands-on practice. For example, Dr. Lamb teaches the concept of additive blending through showing the classic animation Pas de deux by Norman McLaren, which enables students to connect the concepts with an applied skill and to exploit it themselves in video processing. In this way, the students slowly build up skills by examples and practice. Furthermore, in the BAS, hands-on practice entails working in laboratory condition. It involves performing experiments and analysing data in a biology or chemistry lab. But it can also mean teaming up with scientists in a research exhibition or recreating a lab-like condition in an art studio, which is often what we end up doing. In her course on wearable technologies, Dr. Lamb's students learn basic electronic principles to program and use wearable electronic toolkits like LilyPad Arduino, which can be sewn into fabric and mounted with power supplies, sensors and actuators with conductive thread. They are also introduced to technologies related to wireless communication, such as biosensing, thermochromism, and smart materials to explore new forms of art and design. Students form into teams to design garments that may change colour or shape in response to inputs from the environment or from the wearer's own body. And they are encouraged to think about applications that might have benefit to the wider community. This serves to introduce the fourth principle, which is collaborative learning. As we've seen, students in the BAS program are constantly engaging in work at the frontiers of their own knowledge. In this context, it's crucial to develop a nurturing learning environment that encourages them to take risks and to engage in creative trial and error. I can't emphasize that enough. Creating an environment that allows students to fail is critical, as we heard this morning, to creative practice. Part of this is made possible through instruction, but equally important to this is collaborative learning. Collaboration is exemplified in our Skunkworks curriculum, developed by Tobias Klein and Scott Hesselt, and modeled on an innovation concept developed in the aircraft industry by Lockheed during World War II, where a small and loosely structured group developed projects of radical innovation. In Skunkworks, students work collaboratively in a project-oriented and outcome-based learning environment to create works out of smart materials that react in different ways to their environment. Each student is trained in the operation of 3D printing and 2D laser cutters and employs computer-aided design and manufacturing techniques. As they say, using these tools and resources, students created objects that change colour, behaviour, conductivity, temperature and form based on program changes within the displays. The fifth and final principle, which is as much a practice as a principle, is the creation of new media, and is the creation of genuinely new media, which is illustrated in the preceding examples. New technologies offer an unprecedented opportunity to create art out of symbolic systems and materials which have never formed the basis of art before. The commitment to pushing the frontiers of possibility in the kind of art that is made defines the work of many faculty at the school, whether it is in the domain of procedural art, which is Rodriguez's work, 3D printing, Tobias Klein, new 3D projection technologies, Yuling Lam, and human brain interface, Maurice Benayoun. One way to implement the creative development of new media in the curriculum is to place computation into new contexts and environments. Thus, as we have seen, Dr. Lamb teaches classes on device art, wearable computing, e-textiles, painted circuits, kinetic sculptures. However, the idea of creating new media need not involve the production of entirely new artistic media, but also to expand technologically and make technologically mediated versions of established media, like cinema or photography, as is evidenced by some of the outputs in the extreme environment projects. Several challenges remain, of course, for the major, and I've glossed over all the difficulties we have in implementing the kind of program we have. Several challenges remain, however. One is long-term sustainability. Well, actually, they all concern the question of long-term sustainability. One challenge is the need to secure student access to the resources needed for art and science work. For example, laboratories and equipment. Not all science faculties want to collaborate with us. I don't know why, but it's true. Another challenge is the question of is contextual. The idea of art and science is unfamiliar to most people in the larger community. This problem affects the public image of this program. So ordinary citizens don't really know what it is we do. And this is important when it comes to job application and how to justify the very idea of having a degree that's called a Bachelor of Arts and Science. STM is currently engaged in substantial efforts to improve the situation by conducting talks in secondary schools and running various workshops. This summer we're running a workshop on machine learning and art, and I found out that actually we have 270 people have signed up to this workshop, and members of the public, which is quite extraordinary. And this coming January, this is a shameless plug, I'm organising a big conference on computational media arts at the school, which is going to have a very diverse focus on participation by artists and scholars alike. Thank you very much.